My students, guess what we get to do today? We get to solve a combination circuit. I know, you're like, oh my God, so much joy. Because all you've been doing is solving series circuits or parallel circuits, but a combination circuit, boom, bang, pow, pew, 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 puts it all together. And so now we have a circuit with parallel and series in it all at the same time. And we can do this. All we need is Ohm's law and a little bit of knowledge from Days 1's notes. Days 1 notes consisted of telling us what are the things that we do for a series circuit and what are the things that we do for a parallel circuit. Our main strategy for analyzing or attacking a combination circuit is to try to make a combination circuit look like either a parallel circuit or a series circuit and then use that to solve the whole thing. And so first, hopefully we recognize right off the bat that this section right here is a parallel section of this circuit. And then these two are a series section of the circuit. Now I know this is a parallel section because each of these three resistors shares a connection on two sides of it. And I know that this branch over here, R6 and R7, is a series circuit because there's no choice. If you go through R6, you must go through R7. So what we're going to do is we're going to find the equivalent resistance for our parallel section. We're going to find the equivalent resistance for our series section, and then we're going to go from there. Okay, students, now it's time to attack this section of the problem. So what I've done is I've redrawn these three, R1, R2, and R3, as one equivalent resistor, and I've redrawn R6 and R7 as one equivalent resistor. Now it should make sense, and let's do the easy one first. Since R6 and R7 were in series, what we do is we add the resistors, and so the equivalent resistance for the R6, R7 branch is actually going to be 60 ohms. For our parallel section over here, what we're going to do is we're going to use this formula. And so here's how we use this formula. We're looking for the equivalent resistance. And so we do 1 over each resistor. Also, we can do this as if we're going to do it in our calculator. So we can also do 10 to the negative 1 plus 10 to the negative 1 plus 20 to the negative 1. That's how we would do it in our calculator. Up top, we have 1 over 10 plus 1 over 10, which is 2 over 10, plus 1 over 20. We must have the same denominator, so that's 4 over 20 plus 1 over 20 is 5 over 20. If we did this in our calculator, we would end up with 0.25. But unfortunately, we haven't actually solved for the equivalent resistance. What we solved for is 1 over the equivalent resistance. And so what we need to do is flip over both of our answers. Now we have to get the same exact thing. The top way is just using our fraction. So what that sends us to is we have REQ for this is 20 over 5 because we flip it over, and we get 4 ohms for our parallel part. And what we do for this one is REQ is going to be 4 ohms, but what we have to do in our calculator is we do 0.25 raised to the negative 1, and that ends up equaling 4 ohms. So now we have our parallel equivalent, which is right here. We have our series equivalent, and now we reevaluate the circuit that we have. It looks like in this circuit that I'm trying to make a series circuit. How do I know? Because R4 and R8 didn't have any choice. They are always in series. I have no choice. If I leave the battery and try to go through, I always must go through both R4 and R8. So it looks like I'm trying to make a series circuit in here as opposed to a parallel circuit. With that knowledge, I recognize, as I did before, any parts of the circuit that can be combined to get to what I want. And in this case, since I decided I'm going to try to make this whole thing a series circuit, it would make sense to get rid of the parallel part. And so now what I'm circling here is R5 and the R equivalent for 6 and 7. And hopefully you can tell that these two are in parallel. There are two different branches. There is a choice that you can go through. And so knowing that this is parallel, I'm going to use the same formula that I did last time, which is based on the notes from before. And I'm going to get what the equivalent resistance is in R5 and the R6-7 branch. Using my formula, I know that 30 for my equivalent resistance for the two branches that were R5 and R6-7. And lo and behold, I now have a series circuit, and I've basically started to accomplish what I set out to do, and that is to change my combination circuit into either a series circuit or a parallel circuit. Now that I know it's a series circuit, my life gets a whole lot easier. I just apply my series rules for my resistance. I'm going to add all these resistors together, so 4 plus 6 plus 30 plus 10 is 50 ohms. And now that I have 50 ohms, I can start to fill some things in my VIRP chart. So as you can see from my VIRP chart, which I use to just organize my information, I have resistors 1, 2, and 3 looped together because I know that they were originally in parallel. I have resistors 6 and 7 looped together because I know they were originally in series. And lo and behold, that's what it originally was up top. Now that I know that the total equivalent resistance is 50, I can find the total current in this circuit using Ohm's law. And using Ohm's law, which is I equals V over R, what I do is I take 100 volts and I divide it by 50 ohms and I get 2 amps. And so now with those 2 amps, I can actually start to fill in some information in my chart. One of the things that I wanted to notice and recognize is that, as I said before, that's the reason that I was trying to make a series circuit, is because R4 and R8, there is no choice. They are always in series. And since they're always in series, that actually tells me something. That means that I can put 2 amps of current going through R4 and 2 amps of current going through R8. And that allows me to use that to figure out some other things. Again, with Ohm's law, if I don't know any 2 of the variables, I can find a third. And so in this case, I have V equals IR. And so I have I for resistor 4. That's 2 amps, and the resistance is 6. So that means 12 volts must be used up by resistor 4. And I have 2 amps going through resistor 8, and it has 10 ohm resistance, and so 20 volts must go through resistor 8, or 20 volts must be used up by resistor 8. I have the 3 pieces of information for the total circuit. I have the 3 pieces of information for resistor 8. I have 3 pieces of information for resistor 4. And so I can use this to my advantage and find some more information about the equivalent resistance that's happening in these parallel circuits over here and this parallel circuit over here. Because I know the equivalent resistance is 4, and this is a series circuit that I know that 2 amps must be the voltage that goes through this. And I know that 2 amps must go through everything, so it must also go through here. And I must come back to get 2 amps. 2 amps must be the total current flowing through this whole circuit. Well, since I know that there's 2 amps here, and I know that the equivalent resistance is 4, I could find the voltage that is going to be for this parallel circuit. And so the voltage is going to be 2 amps times 4 ohms, and that's going to be 8 volts. And this will be 2 amps times 30 ohms, and that is going to be 60 volts. And lo and behold, I'm still following the rules for a series circuit. If I add up the voltages, it should equal the total voltage. And let's see if I did that correctly. I have 8 volts for the equivalent for the parallel piece for 1, 2, and 3. I have 12 volts for 4, that's 20. I have 60 volts for the parallel part, that's 5, 6, 7. So that would be 80. And I have 20 volts in the series part for resistor 8. And those added together equal 100. And so I'm still completing exactly what I think should happen. This information that I just got from this circuit is really important because since I know that this 1, 2, and 3 is parallel, I can use the concept that I learned from the notes that the voltage is the same across each resistor in parallel to fill that into my chart. And I know that this voltage of 60 volts is the same for each branch of 5 and 6, 7. And so I'm going to use that and fill it into my chart. So looking at the chart, I know that the voltage in 5, right, the 5 branch and the 6 branch must be 60 volts. So let me put that in. And so I know that this 6 and 7 is going to share the 60 volts, so I can't put that in yet. And I know for a fact that the voltage for the 1, 2, and 3 all has to be the same, and we calculated that to be 8 volts. So I'm going to put that in for each one. And so now I know most of my information. Again, if I know 2 out of the 3 things, I can always solve for the third one. And so V equals IR, or I equals V over R, will allow me to solve for the current in 1, 2, and 3, because in a parallel circuit, the current is split. So I know from what we did, 2 amps is coming into this parallel circuit, then it'll be split into 3 pieces, and then it must come back to 2 amps to go through 4. And so 8 divided by 10 is 0.8 amps. 8 divided by 10 is 0.8 amps. And then 8 divided by 20 is 0.4 amps. And if I did this correctly, 0.4 plus 0.8 plus 0.8 should equal the 2 amps in total, because we know that in a parallel portion of a circuit, it shares the current, but the voltage is the same. And we can use that to our advantage. In resistor 5, because we knew it had to be 60 in the branch for resistor 5 and 60 in total for the branch for resistor 6 and 7, I know that the current has to be shared because it's being split. This is parallel. So how much current do I actually get for resistor 5? Well, all I have to do is look at Ohm's law. I know that I have 60 volts and my resistance is 60, so I get 1 amp. And then the current in each branch of a parallel circuit. So now if I know 1 amp is going through the branch for 5, I know 1 amp has to go through the branch for 6 and 7 because the total is 2 amps. And so I know for a fact that I have 1 amp here and 1 amp here. No, I didn't just say 1 amp here. That's a little physics humor. Now again, I know using Ohm's law, 2 out of the 3 things, I can put them together. And so I have 30 volts for R6 and 30 volts for R7, which makes sense because R6 and R7 are on the same branch, and so they must share the 60 that the branch in 5 has. And lo and behold, I filled out all of my V's, my I's, and my R's. The last part would be to find my power, and all I would do to find all the powers in the circuits would be to multiply all of the voltages by all of the currents, and then we'll have completely solved what looked like a really complicated combination circuit by using some basic strategies. The first strategy being to try to make the combination circuit one type of circuit, either parallel or series. I decided to make it series because of resistor 4. And then the next strategy was to break down any pieces into simpler pieces. So I recognized right away that this was a parallel piece, and I recognized right away that this was a series piece, and so I used that to my advantage. Then I used V equals IR if I could to solve for anything, but I continued to break this circuit down until I got to a series circuit, and then I found the total resistance in series. I used that to find the total current,